now that we've looked at how we can implement a linked list by using a linked list class that the user has access to, that an API programmer has access to, and a list iterator that the API programmer has access to, as well as several different classes that the API programmer doesn't have access to, such as node and linked list iterator, both of which are critical for creating this linked list data structure, but which the user never has access to because it's just part of the plumbing of the linked list. We now ask ourselves, how efficient is an implementation of a list done in this way? And so to answer that question, the way computer scientists study the efficiency of data structures is to ask how the efficiency varies based on the size of the list and on what we're asking for when we ask to do different different actions on our object. Okay, so the first thing that we'd like to look at for the efficiency of our linked list is say, hey, how efficient is it to get the kth element of our linked list? So let's say our linked list has n elements in it, and we want to get the kth element, some element in between 1 and n. Well, how long does that take? Well, we know because of the way that we implemented the linked list that we can't go directly there. The way we get to the kth element is we start at the beginning, we create a list iterator, and we walk through k times calling iterator.next as many times as we need to. And just like a hopscotcher, someone playing hopscotch, who wants to get to the 7th square on the hopscotch board on the sidewalk has to go over positions 1, 2, 3, 4, 5, and 6. The same thing happens in a linked list. To get to the kth position, you have to go over k-1 positions beforehand. And so the efficiency of getting the kth element depends on k. It takes k operations to get there, k constant time operations to get there. In the worst case, you ask to get to the last element, element n. And so getting an element from a linked list, we say takes order n or order k amount of time. It varies based on which element you're asking for. Move right. So now, if you have an iterator positioned at a particular place in your linked list, and you would like to add an element or remove an element from it, we say that that takes a constant amount of time. And when I say it takes a constant amount of time, what I mean is that the amount of time it takes to put a new element into our list doesn't depend on how long our list is, because we assume that our iterator is already at the location where you want to insert the element. So it takes a constant amount of time. It doesn't matter how long the list is. It doesn't matter what element you want to insert. You create a new node, you patch up the references, and it's going to take the same amount of time no matter what. If it takes a constant amount of time, we say that's order 1. It's okay if it takes 5 minutes or it takes 1 minute, as long as that amount doesn't vary, as long as it's the same every time. And then we say it's order 1. Move next. Move right. All right, so now we might want to ask, I got to move my mouse again, sorry. Now we might want to ask, hey, what is the efficiency of adding something to the end of our list? Well, that actually takes 2 operations. The operations that it requires walking down to the end of our list and then adding something to our list once we're there. Well, we know that the first part, walking down our list, depends on how long our list is. If we say our list has n elements in it, then that's going to be order n time. It's going to take n times whatever constant amount of work it takes to walk down that list. So it's order n. Once we're there, though, adding a new element or removing it, in this case we're talking about adding an element, so adding an element to the end once we're there takes a constant amount of time. Doesn't matter how long the list is once we're there. And so given that we have an order n operation and an order 1 operation, all we care about is the one that's highest. And we say that's order n, that's an order n operation. Going to the end of the list and doing something there is order n. Now we looked at one particular kind of implementation of a linked list, a simple singly linked list, where our outer linked list class kept track of the first element in our chain and nothing else. Well, what if we also kept, in addition to keeping track of the first element of our list, we also kept track of the last element in our list? Well, if that was the case, then if we wanted to add something to the end of our list, we wouldn't have to walk down the chain. We could go immediately there and add something to the end. So we'll assume that we do keep track of that because it's a straightforward addition to keep track of the end of our linked list. And so we'll say that adding something to the beginning of our list or adding something to the end of our list both take a constant amount of time once you add that last instance variable. Move right. Okay, what about removing something from the end of the list? Okay, this is a little bit trickier because even if we keep track of the last element by adding that additional instance variable, the thing that's difficult about removing something from our list is we actually have to have 2 pointers in our iterator. We have to have a pointer to the thing that we want to remove and the previous element. And if we keep track of the first element and the last element, that's fine, but we're not keeping track of the one that came before the last element. So if we want to remove the last element from a linked list, well, we still have to walk all the way down, in this case, n-1 positions. And then once we get there, we do a constant amount of work to clean up to remove that element, to clean up the last pointer, to clean up the chain as well. So we say that because we have to go almost to the end of our linked list, order n-1, we get rid of that small constant -1. We just say removing something from the end of a linked list is order n, just like getting to the end of our linked list is order n, because we have to walk down the length of our list. The length of our list is n elements, then it's dominated by the length of our list. Move right. Move right. This is just a visualization of what that requires in order to get down to the end of our list. To remove that last element, we have to have both the position and the previous. And so even if we have our first and our last, we have to go down to the end and we have to patch it up. And that requires us to have an iterator along the way. Move right. Now it's possible to make our linked list even more complex. Rather than just having a singly linked list, where each node has a next element and a data element, we can also have each one of our nodes have a previous element. This is called doubly linked list because a node has a reference forward and it has a node backwards. Now this is kind of nice when we want to remove elements, because if at any given moment we don't need to have an iterator that keeps track of where we are and where we were, we can just have an iterator that keeps track of where we are. And if we want to go backwards, we just use the previous reference. If we want to go forwards, we just use the next reference. So it simplifies our iterator, but it complicates the building of our linked list because we have to make sure that all of our next and previous references are chained together correctly on every operation that we do. Move right. In a doubly linked list, removing that last element takes a constant number of steps because all we have to do is use our linked list's last reference and say, oh, last, which was over here, last now is last.previous. And now that we have changed what last points to, rather than saying last.next equals what was last, now we say last.next equals null. And this element gets cleaned up by garbage collection. So with just 2 operations in a doubly linked list, we can remove the last element, regardless of how long our linked list is, because we have these 4 previous and next references in a doubly linked list. Move right. This is a visualization of how that works. And what you have to notice here that makes it more complicated is you have to clean up the previous links. So if we start with our top diagram and we see that linked list.last is pointing to that last element, the first thing that we do is we say linked list.last.previous. That's the one that comes before it. Oh, I guess actually we say linked list.last equals last.previous. So the first thing we do is we update linked list.last. And then we say last.next equals null, causing what was the last element the one that's in the light pink color, to be lost to the garbage collector. Move right. So in summary, we can list the different amounts, the different efficiencies that we get from different kinds of operations. So the operations are listed there on the left. Access an element, add or remove an element once you have an iterator there, add or remove the first element, add the last element, and remove the last element. We can compare how a singly linked list and a doubly linked list work in terms of efficiency. How fast are they? Move right. What we see is that a singly linked list and a doubly linked list both take order n amount of time in order to access an element. Because regardless of whether it's singly linked or doubly linked, we have to walk down our list to get to it. If we want to add or remove an element at a given position, both singly and doubly linked lists take a constant amount of time. Because once we're at a spot, it doesn't matter how long our list is, it's a constant amount of time to patch it up. The first element is a constant amount of time to remove it and patch it up. And assuming that our singly linked list has a pointer to the end, adding an element to the end is a constant amount of time. The big difference between a singly linked list and a doubly linked list is how long it takes to remove the last element. A singly linked list requires order n time, walking down to the end of our list, whereas a doubly linked list is constant time, because we have a pointer to the end and we have a previous link as well. Now these efficiencies are a big deal because let's say our linked list has 1 billion elements in it. Removing the last element is going to take 1 billion units of time in a singly linked list. But in a doubly linked list, it's just going to take 1 unit of time. And that's a huge difference. And it's a difference that's created by a design of our data structure. Because those numbers can get so large, the efficiency of our data structures matters quite a bit. All right, we'll stop there for this lecture. Thank you for your attention.